Hello and welcome to Science Era. In this video, we're going to focus on OpenStack's Chemistry 2E Chapter 4. The main focus of this video will be section 4.2. We're going to discuss and classify three types of chemical reaction, including precipitation, acid-base, and oxidation and reduction. We're going to identify common acid and bases. We're going to predict the solubility of inorganic compounds, and we're going to learn about solubility rules and compute the oxidation state for elements in the compound. So let's begin. Precipitation, reactions, and solubility rule. A precipitation reaction is one in which dissolved substance react to form one or more solid products. Many reactions of this type involves the exchange of ions between ionic compounds in aqueous solution and are sometimes referred to as double displacement, double replacement, and metathesis reaction. The extent to which a substance may be dissolved in water or any solvent is quantitatively expressed as its solubility. A substance can be soluble or insoluble. Soluble substance will dissolve in a liquid completely, and insoluble substance will not dissolve in a liquid and form the precipitates. Next is solubility rules. 5 solubility rules we need to remember are: first one, all common salts for group 1A elements from periodic tables such as sodium ions, potassium ions and lithium ion and ammonium NH4 ion are soluble. Second, all common salts containing acetate or nitrate are soluble. Fluorine are soluble except those of silver, mercury and lead. All compounds containing sulfate are soluble except those of barium, strontium, lead, calcium, silver and mercury. Except for those compounds following the rule number 1, compounds containing carbonate, hydroxide, oxides and phosphates are also insoluble. Let's look at the trick or the rule to remember the trick to remember the solubility rule. If I say acronyms such as CASH and GIA. In CASH and GIA, you need to remember all the letters what they stand for, such as C stands for chlorate, A for acetate, S for sulfate, H for halogen, N for nitrate and G for group 1A elements. These are all soluble in the water, and exceptions are: for sulfates, exceptions are CBS happy. C stands for Ca, B for Ba, S for Sr, H for Hg, A for Ag, and P for Pb. For halogens, exceptions are Hap, Hg, Ag, and Pb. This is the easier way to remember the solubility rule. If you can't remember the mnemonic, then you simply have to learn the solubility rules, all of the solubility rules as it is. For example, simple solubility rules are: nitrate salts are soluble, alkali, group 1A salts and NH4 are soluble, chlorine, bromine and iodine salts are soluble, not Ag, Pb and Hg. Sulfate salts are soluble, hydroxide salts are only slightly soluble, and CO3, CrO4, 2, PO4, 3- salts are insoluble. Let's look at an example. Predict the result of mixing reasonably concentrated solution of the following ionic compound. If precipitation is expected, write a balanced net ionic equation for the reaction. So number 1 they have given us is potassium sulfate and barium nitrate. Two possible products for this combination are KNO3 and BaSO4 if you write the chemical equation as whole. The solubility guideline indicates that BaSO4 is insoluble and or we can say barium sulfate is insoluble, and so a precipitation reaction is expected, and the net ionic equation for this reaction derived in the manner will give you Ba2 plus SO4 2 minus, and so it will give you barium sulfate uh, in solid state. Next is lithium chloride and silver acetate. Two possible products for this combination are also possible. Among the two, we know that AgCl, silver chloride, is insoluble, and so the precipitation reaction is expected for this compound too. And the net ionic equation will be as follow. Ag plus Cl minus will give you AgCl in solid form. Next is lead nitrate and ammonium carbonate. Again, two possible product combination are possible, and from the solubility guideline, we know that lead carbonate is insoluble and the precipitation reaction is expected. And the net ionic equation is given as follow. Pb2 plus carbonate CO3 2 minus ion will give you PbCO3. Acid-base reaction. An acid-base reaction is one in which hydrogen ion is transferred from one chemical species to another. They are important in production of fertilizers, pharmaceuticals. They're important in chemical transformation that take place within the cell and as well as in lakes and oceans. An acid is a substance that will dissolve in water to yield hydronium ion, H3O plus ion. For example, HCl is a strong acid. It dissolves in water to give you chloride ion and hydronium ion. A base is a substance that will dissolve in water to yield hydroxide ion OH minus ion. The most common bases are ionic compound composed of alkalis or alkaline earth metal cations in group 1 and 2 of periodic table combined with hydroxide ion, for example sodium hydroxide or calcium hydroxide. Next is a neutralization reaction. It is a reaction, it is specific type of acid-base reaction in which the reactant are an acid and a base but not water, and the product are often salt and water. So we can simplify it as neutralization reaction is the reaction of acid and base which give you salt and water as a product. An example of neutralization reaction is magnesium hydroxide, which is an base, and magnesium hydroxide, which is an acid, and HCl, which act as base, will react to give you magnesium chloride salt and H2O. Strong versus weak acid and bases. Strong acids are acids that completely dissolve or dissociate in water and produce hydronium ion, whereas weak acids are only partially react with water, leaving a large majority of dissolved molecule in their original form and generating a relatively small amount of hydronium ion. Example of strong acid include HBr, HCl, HI, and H2SO4. An example of a weak acid is acetic acid. Strong versus weak base. A strong base dissociate completely to produce cation, whereas weak base only react partially to produce in a reaction. They only react partially. For example, ammonia is a weak base. Example of strong bases include KOH, sodium hydroxide, calcium hydroxide, and barium hydroxide. Okay, so let's look at an example. They are here asking you for the weak acid, which is hydrogen hypochlorite. When they react with water, what is the balanced chemical equation for the acid-base reaction? How are we going to go about this question? So the two reactants are provided, HOCl hypochlorite and water. Since the substance is reported to be an acid, its reaction with water will involve the transfer of hydrogen ion from HOCl or hypochlorite to water to generate hydronium ion H3O plus and a hypochlorite ion OCl minus. So we're going to write hypochlorite plus water on the reactant side and OCl minus and H3O plus ion on the right hand side, because we are producing those ion. Those are the products. Hypochlorite ion and hydronium ion are the product, and HOCl or hypochlorite and water is the reactant. A double arrow is appropriate in this equation because it indicates that hypochlorite is a weak acid and that has not completely reacted. So the reaction can proceed in both directions. In second part, they ask a solution of barium hydroxide is neutralized with solution of a nitric acid. So we're going to write a balanced chemical equation for a solution of barium hydroxide which is neutralized with solution of nitric acid. The two reactants are provided, barium hydroxide and nitric acid or HNO3. Since this is a neutralization reaction, the true products will be water and salt, because in neutralization acid and base reacts to form water and salt. Water and salt composed of cations of ionic hydroxide Ba2 plus and anion generated when acid transfer its hydrogen ion which is NO3 minus. So the equation will go about barium hydroxide plus 2 molecules of nitric acid will react to form barium nitrite and water, 2 molecules of water. Notice that there is only a single arrow in between reactant and product. This means that reaction only proceeds in one direction. This is a neutralization reaction, so it will produce salt and water. Oxidation reduction reaction. The term oxidation was originally used to describe chemical reaction involving oxygen, but it was evolved and referred to as the broad term of oxidation and reduction reaction. Oxidation means loss of electrons and reduction means gain of electron. The species that is oxidized is called a reducing agent, and the species that is reduced is called oxidizing agent. Some redox reaction involves the transfer of electrons between reactant species to yield ionic product. Such reaction between sodium and chloride, for example, reaction between sodium and chlorine, it yields sodium chloride. It is helpful to view the process with regard to each individual reactant, that is, to represent the fate of each reactant in form of the equation called half reaction. So here you can see the half reaction for sodium, which is producing 2 sodium ions and 2 electrons, and chlorine reaction which is producing 2 chlorine ions. This equation shows that sodium atom loses electron while chlorine atom gains electron, and the S subscript for the resulting ions signify they are present in the form of solid ionic compounds. For redox reaction of the sort, the loss and gain of electrons is defined the complementary process that occur. So as I said before, oxidation is loss of electron and reduction is the gain of electron. Therefore, sodium is oxidized and chlorine undergoes reduction. As sodium loses an electron, so it is oxidized and it is a reducing agent. And chlorine gain electrons, it is an oxidizing agent. The oxidation number or oxidation state of an element in a compound is the charge its atom would possess if the compound was ionic. Let's look at the difference between the element which is reduced and element which is oxidized. If an element is reduced, it gains electron, oxidation number decreases, and the substance is classified as an oxidizing agent. And if an element is oxidized, it loses electron, oxidation number increases, and the substance is classified as a reducing agent. Oxidation number rules. There are some rules we need to follow in order to give an oxidation number to an element. Rule number 1. Oxidation number in free element is 0. For instance, oxidation number of calcium and zinc is 0. This also holds true for diatomic elements such as oxygen, chlorine found in nature. Rule number 2. In simple ions, the oxidation number is same as the charge on the ion. For instance, the oxidation number of magnesium is 2 plus and the oxidation number of bromine is minus 1. Rule number 3. Oxidation number of group 1 metals in a compound is a plus 1 and for oxidation number for group 2 metals is plus 2. Rule number 5. The oxidation number of hydrogen in a compound is usually plus 1 except when hydrogen is bonded to a group 1 metals to form metal hydride, oxidation becomes minus 1. Rule number 6. The oxidation number of oxygen in a compound is usually minus 2 except when found in peroxides. H2O2 is a minus 1. Rule number 7. Oxidation number of fluoride is always minus 1. In a neutral compound, sum of the oxidation number of atom is 0. Let's look at an example. Example is asking you to follow the guideline in this section and assign an oxidation number to all element in the following species. So species number 1 we have is H2S. We know that according to the guideline 1, oxidation number of H is plus 1. It is plus 1. Therefore, using the oxidation number and compounds formula, we can use it to calculate the oxidation number of sulfur. So, the charge on H2S will be 0 equals we have 2 hydrogen and oxidation number for hydrogen we know is 1, so we will multiply 2 hydrogens time plus 1 oxidation number of hydrogen, and then we have 1 sulfur. Okay, we're going to add this. We have 1 sulfur, we're going to time it. We don't know the oxidation number of sulfur, so I will say it is X. In next step, X will be equal to 0 minus 2 times plus 1 equals minus 2. Therefore, the charge on the sulfur is minus 2. So, sulfur charge is minus 2. So, to find the oxidation number of each element in the compound, we're going to time that element with its oxidation number according to the rules. And if we don't know the oxidation number of any element, we're going to say it as an X. And then we solve for X to find the oxidation number of that certain element. Let's look at example number 2, which says SO3 2 minus. So I'm going to erase this first. Okay, so Okay, again from the rule, we know that oxidation number of oxygen is always -2. For I'm going to solve for SO3 2 minus. Then charge on SO3 2 minus will be -2 equals 3 oxygen times the charge, which is -2, plus 1 sulfur times, we don't know the charge on sulfur again. Then we solve for X, and I will get is +4. So the charge on sulfur is +4. Why I wrote -2 here is because it is SO3 2 minus. So this 2 minus will come here. In this example, when we were solving for H2S, the equation was equal to 0 because they don't have a charge. Next example, they asked us to solve for what? Na2SO4 minus. Sorry. It's example number C. So it was Na2SO4. Right, this is an ionic compound. For ionic compounds, it is convenient to assign oxidation number for cations and anions separately. According to the guideline, the oxidation number for sodium is +1. And then we're going to solve for oxidation number of SO4. Assuming the usual oxidation number for oxygen is -2, the oxidation number for sulfur is we're going to calculate. So we know that oxygen is -2. We're going to solve for sulfur. We don't know what is sulfur. So charge on SO4 minus SO4 2 minus will be -2 for this oxygen equals 4 oxygen times the charge of oxygen, which is -2 again, plus 1, and then we're going to time it with the X. Right. In next step, we're going to solve for X. So X will be equal to -2 minus 4 times -2, which will give you +6. So we know sodium, we have charge +1. For sulfur, we calculated the charge is +6, and we assumed that for oxygen the charge is -2 according to the guideline. Therefore, we solved this question. Single displacement reaction. Single displacement or replacement reactions are redox reaction in which an ion in solution is displaced or replaced via oxidation of metallic element. One of the common example of this type of reaction is acid oxidation of certain metal. For example, zinc react with 2HCl to form zinc chloride and H2 gas. Metallic elements may also be oxidized by solution of other metal salt. For example, copper plus AgNO3 will give you CuNO3 plus 2Ag. This reaction may be observed by placing copper wire in solution containing a dissolved silver salt. Silver ions in solution are reduced to elemental silver at the surface of copper wire, and resulting copper ions dissolve in the solution to yield characteristic blue color. As you can see in the figure A copper wire is shown next to the solution containing silver ions. In figure B, displacement of dissolved silver ion by copper ion result in C. Accumulation of grey colored silver metals on wire and development of a blue color in solution due to dissolved copper ions. Let's look at an example describing redox reactions. Identify which equation represents redox reaction, providing a name for reaction if appropriate. For those reactions identified as redox, name the oxidant and reductant. So in example 1, zinc carbonate give you zinc oxide plus carbon dioxide. Redox reactions are identified per definition if one or more elements undergo a change in oxidation number. So in A, this is not a redox reaction because oxidation number remains unchanged for all the elements. Example number B, 2Ga liquid plus 3Br2 will give you 2GaBr3. Ga stand for gallium. This is a redox reaction. Why? Gallium is oxidized. Its oxidation number increased from 0 in Ga to plus 3 in GaBr3. The reducing agent is Ga liquid. Bromine is reduced. Its oxidation number decreased from 0 in Br2 to minus 1 in gallium bromide. The oxidizing agent is Br2. In next example, methane react with oxygen to give you carbon dioxide and water. This is also a redox reaction. It is particularly interesting process as it involves the same element oxygen undergoing both oxidation and reduction. So this is called disproportionation reaction. Oxygen is oxidized, its oxidation number increased from minus 1 in H2O2 to 0 in O2. Oxygen is also reduced. Its oxidation number decreased from minus 1 in H2O2 to minus 2 in H2O. For this proportionation reaction, the same substance function as an oxidant and reductant. Balancing redox reaction via the half reaction method. A systematic approach have been developed to assist the process in balancing the equations. In step number 1, write the two half reactions representing the redox process. Then balance all elements except oxygen and hydrogen. Balance oxygen atoms by adding H2O molecules. In next step, balance hydrogen atoms by adding H2 ions. Then balance charge by adding electrons. If necessary, multiply each half reaction coefficient by smallest possible integer to yield equal number of electrons in each. Add the balanced half reaction together and simplify by removing species that appears on the both sides of the equation. For the reaction occurring in basic media, carry out these additional steps. Number A. Add hydroxide ion to both sides of the equation in number equal to the number of H plus ion. On the side of the equation containing both H plus and OH minus ion, combine these ions to yield water molecule. Simplify the equation by removing any redundant water molecules. Finally, check to see the both number of atoms and total charges are balanced. Let's look at an example. Writing a balanced equation for reaction between dichromate ion and iron 2 to yield iron 3 and chromium 3 in acidic solution. They have given you the equation for it. In step number 1, we're going to write down the two half reaction. Each half reaction will contain one reactant and one product with one element in common. So Fe2 plus will give you Fe3 plus and Cr2O72 minus will give you Cr3 plus. In next step, balance all elements except oxygen and hydrogen. The iron half reaction is already balanced, but chromium half reaction shows two chromium atoms on the left and one chromium atom on the right. Changing the coefficient on the right side of the equation to achieve achieves balance with regard to Cr atom. So we change the chromium side, we added 2 here. In next step, balance oxygen atom by adding water molecules. The iron half reaction does not contain oxygen atom. The chromium half reaction shows 7 oxygen atoms on the left and none on the right. So we're going to add 7 water molecules on the right side. So we added 7 water molecules on the right side to balance the oxygen. In next step, balance hydrogen atoms by adding H plus ions. The iron half reaction does not contain H atom again. The chromium half reaction shows 14 H atoms on the right and none on the left. So 14 hydrogens are added to the left hand side. 7 times 2, 14 hydrogens on the right. We added 14 hydrogens on the left hand side to balance the reaction. In next step, which is step number 5, we're going to balance charges by adding electrons. The iron reaction shows a total charge of 2 plus on the left side and 3 plus on the right side. Adding 1 electron to the right side brings the total charge to 3 plus 1, which is equal to 2 plus, and charge balance is achieved. The chromium half reaction shows a total charge of 12 plus on the left side. The total charge on the right side is 6 plus. 2 times 3 plus chromium ion. Adding 6 electrons to the left side will bring that side's total charge to 6 plus, and charge balance is achieved. So we added one charge on the right hand side to balance the iron, which will give you 3 plus plus minus 1. We adding one charge on the right hand side will give you 2 plus. So we know that the ion is balanced on the either side. We got 2 plus charge on the right side and we got the 2 plus charge on the left side. Now look at the chromium ion. We know that chromium on the right hand side have 6 ions or 6 electrons, and on the left hand side it got 12. How? Let's look at it. 1 times 2 minus plus for hydrogen 14 times 1 will give you 12 plus. So we know that we have 12 plus electrons on the left hand side, but 3 plus times 2, which will give you 6 electrons, 6 plus electrons on the right hand side. So what we're going to do is we're going to add 6 electrons on the left hand side, so which will give you 12. We already have 12 plus on the left hand side. We're going to add 6 minus electrons, which will give you 6 plus charges on the left hand side. So the equation is balanced. In the next step, we're going to multiply two half reactions. So the number of electrons in one reaction equals the number of electrons in other reaction. To be consistent with mass conservation and the idea that redox reaction involves the transfer of electron, the iron half reaction coefficient must be multiplied by 6. So we're going to multiply iron half reaction with 6 on the either side of the equation. In the next step, add the balanced half reaction and cancel the species that appear on the both sides of the equation. So we're going to cancel out the species that appear on the both sides. So 6 minus we're going to cancel out. Only the 6 electrons are redundant species. Removing them from each side of the equation will yield the simplified balanced equation like this. Now let's confirm the atoms and charges are balanced on either side of the equation. So using the table, we can see that we have 6 iron electrons, iron reactant, and 6 iron product. Chromium, 2 reactants. Even in the product we have 2 reactant. For oxygen, 7 oxygen in the reactant and 7 oxygen in the product. 14 hydrogens in the reactant and 14 hydrogen, 7 times 2, 14 hydrogen in the product. Total charge on the right hand side and the left hand side is 24 plus, which means that the equation is balanced. Remember, in disproportionation reaction, the element on the both side is oxidized and reduced. What we learned in this video: classifying chemical reaction. Chemical reactions are classified according to the similar pattern of behavior. A large number of important reactions are included in 3 categories: precipitation, acid-base, and oxidation and reduction reaction or redox reaction. Precipitation reaction involves the formation of one or more insoluble product. Acid-base reaction involves the transfer of hydrogen ion between reactant, and redox reaction involves a change in oxidation number of one or more reactant element. Then we see writing balance equation for some redox reaction occurs in aqueous solution is simplified using a systematic approach called half reaction method. This brings us to the end of classifying chemical reactions. Thank you for watching. If you like my video, don't forget to subscribe.